Recording in progress. Yeah, comes on everyone. Let's start off. Last class we are done with laws of motion. We'll be starting off with friction today. Yeah. Comes on everyone. So the chapter, right, has a lot of similar thing. It's almost laws of motion except for one additional thing. Others, you need to keep your cams on. You guys are not able to hear me or something. Okay. Able to hear me, right? Hannah, Manav, able to hear me? Okay. Okay. Let's go ahead with this. So what is friction about? So when two surfaces are in contact, there is an opposition. To relative motion. Between the surfaces. This property is called friction. So the whole thing, right? You can just classify with this one thing. Huh? This is the main word, opposition to relative motion. That's it. That is the whole driving factor behind this chapter. Right? So we'll talk about that. So what friction does, friction, right, doesn't care about whether you're moving or not. Friction worries only about one thing. Is there a relative motion with respect to me? If there is a relative motion, I don't like it. Right? Most people, right, the most misconception is this: friction opposes motion. Not necessary. For example, let's think of like this. When you're walking, what is the direction of friction? When you're walking, what do you think is the direction of the friction? Forward or backward? Any guesses? No, generally what we think, right? It's backward. Now, then if you think it is backward, then the question comes like this. Then who is making you go forward? If friction is backward, remember, you need force to go forward, isn't it? If friction is backward, then who is making you go forward? Someone has to make you go forward. So the problem was this. When you're walking, right, just visualize how your leg goes. When you're walking, if this is your leg, right, you're swinging it backward. When you're swinging it backward, look at the point at the bottom. This point here is trying to go backward. It's trying to have velocity be forward. When it is touching the floor, so this point, the foot, right, is actually trying to go backward. You might be walking forward, but your leg, right? If there was no friction, if the floor was smooth, your leg would have just gone backward. The heel is trying to go backward. And friction doesn't like this because the ground is at rest and your leg is going backward. The friction actually comes forward. So friction is actually responsible for you to walk. The reason you're able to walk is because of friction. So be careful with that. Friction opposes motion is a wrong statement. Friction opposes a relative motion. We'll talk more about that. So keep that in mind. Friction does not oppose motion. Friction opposes a relative motion. Yeah, friction can sometimes support motion, oppose motion, but it will always oppose relative motion. It can support or oppose motion. And let me take one more example. When you're going on a cycle, right? When you're riding a cycle, can you tell me what is the friction cut direction on the back wheel and the front wheel? When you're going on a cycle, what will be the direction of friction on the front wheel and the back wheel? What do you guys think? So again, you have to go back to the how the cycle works. Now, if you look at your cycle, so this is your cycle there and just drawing. So you have that pedal kind of thing there, and like this is connected somewhat like this. You have your pedal. Now see what you're doing actually. When you're putting your foot on the pedal and you're pushing it, what you're doing, you're actually rotating the back wheel. Did you ever do this thing? I don't know whether you did this thing. You kept the cycle on a stand, right? And then rotate the pedal with your hand, and then you just left it. Did you ever do that? Did you ever do that? Never did it. You put your cycle on stand, okay? That means make sure the back wheel is not touching the floor. Then with your hand or something, just rotate the pedal fast. Then the back wheel starts rotating. Now suddenly put it on the ground. The cycle just goes off. Did you ever do that? So what is happening, right? So when you're rotating, when you're cycling, right, you're pushing it, the back wheel is trying to rotate backward. So this point here, the back wheel ka base point is actually going backward. It's trying to go backward. So when we pedal, we are rotating the back wheel. You're not giving any power to the front wheel. Right. And so the point in contact is trying to go backward. It is trying to go backward, right? It might not go backward. The point in contact is trying to go backward. Just like when you're walking, your heel was trying to go backward. And if you look at here, so the friction will be forward. But what about the front wheel? Now, front wheel ka scenario is different. The front wheel, right? Because the back wheel is trying to go, the back wheel is pushing the front wheel. So if you look at the front wheel ka scenario, the front wheel doesn't want to do anything. This rod is pushing it. The front wheel is being pushed forward. Meaning the point on the front wheel is actually trying to go forward. So the back wheel and the front wheel, right? They have a completely different tendency there. So this point is trying to slide. The friction will be backward. Yeah, the friction will be different though. So on the back wheel, the friction is forward. On the front wheel, friction is backward. If you apply brakes, then the friction will be back for both of them. But when you're pedaling the cycle, this is what is actually happening. Meaning, I'll give you another example of this thing. Think of like this. Let's say you're pushing your friend. Your friend does not want to go, but you're trying to, usko push karke aage leke ja raha hai. So like this, your friend doesn't want to go. And you're like, no, you have to come. You're pushing them. Can you tell me how will the frictions be on you and your friend? Just imagine yourself, okay? You don't want to go. You're just standing and someone is pushing you from the back. How will the friction be? Backward, right? This is your front wheel. The front wheel doesn't want to go. And what about you? If you're pushing your friend a lot, you will try to slide backward. Your friction will be forward. This is the back wheel. Exact same thing is happening when you're riding a cycle. Is that making sense, everyone? The spokes, right? So there must be some rod or something which is connecting the front wheel to the back wheel. If you don't, that beach mein hota hai na, I didn't draw the picture properly, but you have that entire steel frame, isn't it? That steel frame is pushing it. Is the story clear, everyone? So if you look at a car, right, even cars have the same thing. Ever heard about a four-wheel drive? All the cars you see on the road, right, most of them are two-wheel drives. That means the engine is only connected to the back two wheels. There is no power to the front two wheels. So if your wheels get stuck, right, the back two wheels are stuck ho gaya. No matter what you do, the car will not come out only because the front wheels don't have any power. So these are called two-wheel drives. The cars and everything, right, they get transmission only to the back wheels. If you look at all army vehicles, right, they're four-wheel drives. The power is transmitted all the four wheels because army vehicles, right, they travel on places where there are no proper roads and everything. So they need more transmission and more power. These things are more stable, but more expensive because you're giving power to both front and back. Engine has to be powerful and more expensive. So normal day-to-day to use, we use only two-wheel drives. So that's a four-wheel drive. So if you make a cycle with a two-wheel drive, मतलब सोचो यहाँ पे pedal ना, if you connect it to front wheel also somehow, then both the frictions will be forward. You can create a cycle like that. But in this case, when you rotate the front wheel, right, the chain will start blocking you. It creates all other issues. Not a great idea there. So that means in Bollywood, right, if you see the typical movies, you will see something. Yeah, four-wheel drives they're expensive. It is maintenance a problem, and you have to put a lot of new stuff into the vehicle. So let's say someone is trying to run on a vehicle and you want to stop the vehicle. One of the best way to do, you know what? Somehow, if you can lift the back wheel, I know which is tough, but if you can lift the back wheel, the car will not move. Let me show you how it looks. Very typical. You will see this in movies. Actually, heroes do this stuff. Where are you? The quality is not great, but I hope you can see. There is this movie of John Abraham.
1000-1500 फ्लैट तो बन ही जाए। वो तो ठीक है, लेकिन मनोहर का क्या? मनोहर तो मैं संभाल छोटी बिना होती है।
So we have John Abraham there. There is a fight. I'll not get into it. You must have seen the movie Force. We'll get to the main thing. So there is a fight. Our hero removes the shirt, standard. And then the goons are trying to run away in the car. There. Look at this scene here. There. Did you see what is happening with the back wheel? This guy went and just lifted the back wheel. You can see no matter how much they accelerate, the wheel is just rotating. Nothing goes forward. There. There. Look at the back wheel. Not his back wheel. And now see, he says, no, chhod do karke. Now see, this is what I was saying. What happens if you leave now? Now if he leaves, right? There it goes off. So this is what I was saying about that cycle thing. If you rotate the back wheel and suddenly leave it, right, it'll just go off. The friction would suddenly So that's a two-wheel drive car. That is the reason, no matter how much that Gunther accelerating, right, it doesn't go forward. Yeah, lifting was difficult. But let's say somehow if you could lift, that's a better way to stop a car. So lift the back wheel and there'll be no power transmission there and you're stuck. Clear with this. So that's a little introduction about like friction. So the main thing is that friction, right, actually makes you walk. It's really not that bad thing as people portray it. It is a necessary evil. The next thing, so why do we get this friction in the first place? So there are two reasons why we get friction. At least there are two theories people accept so far. One is interlocking. The second thing is cold welding. The first thing is interlocking. The word itself is self-explanatory. So when you look at the surfaces, right, even though they look very smooth, they're not actually smooth. Meaning your skin, right, which you might think like, oh, my skin is so smooth and beautiful. If you actually take a microscope and zoom in, you will get a bit disgusted with your skin. Like nighttime when you're sleeping, there are small germs which actually come out of your skin pores and they're just walking around and they sleep and they chill out and everything. So there is a whole ecosystem on your face. So never look at your skin with a microscope. You will really feel great about it. It's a common thing. Your body actually has more bacteria and all other stuff than your own cells. But anyway, so when you actually zoom into a surface, right, you will see something like this. They're interlocked. Ever seen a sandpaper? They use this paper to scrub the painting of something like very rough. That's an extreme case kind of thing. So when you actually zoom into a surface, you will see the surfaces are pretty rough. They get locked with each other. The hills and the valleys get locked up. Surfaces are interlocked at molecular level. The second thing is cold welding. This is the most accepted thing. So here the idea is when you say two surfaces are touching, in reality, right? Meaning think of like this. Try to put a namaste with both your hands, right? And tell yourself, are the both the hands touching at every point? Just look at the between them. You'll see a lot of empty spaces, isn't it? So if you look at your hand when you put a namaste kind of thing, you will see actually your hands are really not touching everywhere. It is touching at very few points. So even though we say two surfaces are touching, in reality, the points of contact are very few. It is like imagine you standing on your toes. It puts a lot of pressure on your toes. All your weight is going at few points. This is roughly 1 in 10,000 approximately. So for every 10,000 molecules, there's only one molecule which is touching on the surface. So this puts a lot of pressure on these surfaces. And due to such a high pressure, these two molecules start forming a covalent bond. They start van der Waals forces and all that stuff. I'll not get it, but roughly 1 in 10,000 points are in contact. So literally all the surfaces are not touching with each other. And this leads to high pressure. You're putting all your weight on few points. Right? Which creates bonds. This is called cold welding. This is what actually happens in a welding. In a normal welding, right? You heat up the metal to high temperature and the molecules get stuck. So this is called cold welding because you're not using high temperature, but you're still forming bonds. These bonds are called cold welding joints. So when you take two surfaces, so let's say the block ka mass is m. This is a smaller area. Let's say we have a more bigger block. Again, identical surface. Well, let's say mass is m. This is a larger area. Maybe the density is different, or maybe the height of the block is different. So now if you look at here, maybe we find three cold welding joints here. Here we have 1, 2, 3, 4, 5, 6. There are more joints here. So here what is happening? Because the mass is same, you get a higher pressure because there is a less contact points. The entire weight is balanced by 3 points here. This leads to higher pressure, which will give you stronger bonds. Here, the same weight is distributed over 6 points, so we have less pressure. So the bonds are weaker, but you have more bonds. So friction is independent of surface area. As long as the weight is same, it doesn't matter whether you're touching at half the surface area or full surface area. Friction is independent of surface area. Yeah, but in real life, what happens? When you put a very little surface area, right, it starts cracking. That whole part breaks down and the surface actually changes. That is a problem. So practically area does matter, but theoretically, if assuming the surface doesn't break or crack or doesn't get destroyed, it shouldn't depend actually on the area. So if you put a lot of pressure on a small area, it does crack. Second thing, this is something even more weird. Now, if you actually start polishing a surface, if you take a surface and you start polishing, initially friction decreases. But if you continue to polish, the friction suddenly starts going up. So initially, interlocking decreases. When you are polishing a surface, you are decreasing that hills and everything, valleys. So the interlocking decreases. The friction drops. You are basically messing up the nature of the surface only. So friction decreases. But if you continue to polish, more and more surface points will start coming in contact. Suddenly, the cold welding increases. So when you rub a surface, right, it is not the same surface as previously. It changes, the interaction, it changes, friction changes. This previous one was if the two surfaces are identical surfaces. When you polish a surface, it is not the same thing anymore. Friction decreases, and if you polish further, the friction actually increases pretty fast. Cold welding increases, more and more points will start interacting. So actually, smooth surfaces have very high friction. But entire NLM, right, entire loss of motion, we kept on saying smooth surface, smooth surface. In reality, we should have said frictionless surface. Yeah, it will be more than initial. Friction can go really high. So this is also called as, friction welding. Basically, there is a way to connect two things. So if you take two copper plates and if you polish them really high, Muka value goes really high. They literally stick to each other. You can get even more friction than before. So smooth surfaces are actually not a good idea. They have really high friction. So be careful with that. When they say smooth surface, they're actually talking about frictionless surface. The friction would drop like this and then rapidly go off. So smooth surfaces actually have high friction. How does a perfectly smooth surface look like? Can you imagine how a perfectly smooth surface look like? When I say this, people think of flat, white kind of surface, like it's flat. But in reality, a smooth surface doesn't look like this. Imagine like this, a box of laddus. Imagine you have a box and let's say इसमें मोतीचूर laddu hai. So that each laddu is a molecule, right? They have a bond between them, lattice in 3-dimensional. So a smooth surface is actually nothing but like, it looks like a big box of motichur laddus. Now, if you take another motichur laddu box and if you keep it on top of it, what do you think will happen? They will start forming bonds in the 3-dimension, isn't it? Like this. The two surfaces will just stick to each other. That means if you take two blocks, perfectly smooth surface, and if you just take them and attach them, they will combine to form one big block. You can't separate them. They just become one block. The reason why you don't see this in real life is because when you actually try to make a smooth surface of any metal, right, because of oxygen, it forms a ferrous oxide layer on top. So you have to do this in a perfect vacuum and you have to make sure the surfaces are perfectly smooth. Then if you cut it and join them, they'll become again back into one block. Yeah, theoretically, we can do that. So then next time when you think of a smooth surface, imagine a box of laddus, a big flat surface filled with laddus. Each laddu is a molecule. So there's nothing like, when I say flat surface, you guys are imagining something like, your computer screen or A4 sheet paper. It doesn't look like that. So if you put one more on top of it, they do get stuck. So, but be careful when we say smooth, we are actually saying frictionless surface. So smooth surface is actually wrong word, but yeah, then again, we use it everywhere. The actual word is frictionless. So that's a bit about it. Next thing. So we know what is friction. We know why it comes. So like I said last time, friction, right? There are primarily only two things. If I know what is the direction of friction and if I know the magnitude of friction, my job is done. After that, it is completely NLM. So first thing, let's find the direction of friction. Step one, this is what we do. Whenever you want to find the direction of friction, start with an assumption. Assume surfaces are frictionless. So if you want to see the true nature of the friction, you should start with an assumption there is no friction and see how things would behave. Right? It's like asking, how do you know a person is honest? Or how do you know a person is good? It's like if a billionaire, right, comes and gives you 1 lakh rupees donation, is it really a great thing? Right? A billionaire comes and gives you 1 lakh rupees, right? Donates the 1 lakh rupees. Is that really a great thing? You might feel like, yeah, it is a good thing. So, but what if a beggar on a road, right, has eating food and a dog comes and he gives all the food to the dog and he stays hungry? So the thing is, your true nature comes out when things are actually bad. So that's who you are actually. So that's what I keep telling, when people say, oh, sir, bahut tough ja rahe, I'm finding difficult. Yeah, that's the time, when your true character shines. Are you going to fight back or are you going to keep cribbing about it? So fight back. That is how character gets built. When you have everything, everyone will behave like, things are awesome. Yeah. If the true nature of anyone comes out when things are bad. So I keep telling these people that, normally, uh, when you want to know how good is your friend, when someone says he's your friend and everything, right? Or even when two people are getting married, right? The best thing to do is let them go on a trek with a group of people, 2025, let them go on a trek for 3 days. You will see the true nature. Ever been on a trek for 3 days in a forest with a group of 20 people or 30 people? It is hopeless. You don't have bathrooms. You're running behind a tree. You're eating anything that you're getting. I have been on a trek like that for 3 days. It is raining. There is a mud. You keep falling down. You get exhausted. It is hopeless. And you just keep walking every day for 8 to 10 hours. So that is the thing. You will see how true a person is. So, anyways, if it's difficult here. Next thing, so what we see here, we see the tendency of the surface system. So first assume there is no friction. Then next thing, now once we know how the surface are trying to move, then we will see what the friction would have done. Apply friction in such a way it opposes relative motion. That's it. Friction has only one role in life. It doesn't like relative motion. That's the question you should always ask. What is the relative motion, not which way you're going? I'll give you one or two ways to think about it. Remember like this. I'll give you an example. So let's say we have a person A and we have a person B, and you're in the middle. So you are friction, okay? You are the friction. And you have only one job in life. Your only job in life is to make sure A and B are together. Okay? That's your whole purpose in life. Now let's say B starts running at 10 meters per second. What can you do? Think of what all things can you do to keep A and B together. One, stop B. Right? Second, forget about B. Let A also run with 10 meters per second. See, my job is to keep them together. I never said you to stop B. Stopping B was only one of the options. Or decrease the speed from 10 to 5 and increase the speed of A to 5. These are the three things I can do, isn't it? I can stop B, or I can forget about B and make A go with 10, or I can decrease the speed of B and increase the speed of A. Is that making sense? So these are the three ways I can keep A and B together. Is that making sense? That's what a friction does. Friction will see, okay, which option is good. And it will always choose the third option because Newton's third law. Whenever you try to stop the guy in the front, I get a force. I can use that force to increase the speed of the back guy. Now, the other way to think of, this is more technical, but you'll understand this better. Think of this friction like a springs. Yeah, technically they're springs. The bonds are like springs. So if you have two surfaces A and B, think of these cold welding joints like springs. That's a very good, analogy. Like you can think of a bond like springs, and that will help you to see. So we'll use the spring analogy. Cold welding joints, we can treat them like springs between surfaces. And you know what springs do? They always want to be in natural length. Great. So let's see what happens. Case one. Listen to these cases. These cases will make things clear. Let's say we have two blocks, A and B. Let's say A is going with 2 meters per second. B is going with 1 meter per second. This is the rough surface. So the question is, what is the friction between them? Which direction? We don't want the magnitude. So think of like this. If there are springs between them, the guy A is going faster. Now, you tell me, no? A and B are going like this. As a friction, what was your job to do? What will you do? A is going faster, stop him. B is going slower, help him. Isn't that what you do? So now, if you think of them like springs, so see how the springs will be. The springs will look like this. The springs will stretch. And what will the springs do? They pull. So on A, the friction will be backward. On B, friction will be forward. Understood the logic? If there is no friction between A and B, A would have gone ahead and B would have stayed there. Matlab B would have gone slower. So friction will oppose A and support B. That's it. That's the whole idea there. Suppose A is going with 1 meter per second and B is going with 3 meter per second. Now what would have happened? A would have been slower and B would have gone forward. Now the springs will look like this. The springs are stretching, right? So they will pull. So AMA friction will be forward and BMA friction will be backward. Are these two cases making sense, everyone? Case 3, what if this guy is going with 2 meter per second and this is also going with 2 meter per second? Now what happens? If you and your friend are catching hands and both are running with the same speed, will the hands ever get stretched? The hands will be always loose, right? So the springs will never stretch, only friction is zero. So even though the friction is rough, it does not mean there will be a frictional force. If you're already going together, why will I come and mess up it, right? What was my job? To make sure you both are going together, and you're already going together. I'm happy, so I won't act only. Just because you're rough does not mean you will act always. What about now? Always imagine it is you in the middle and both the friends are there. One guy is going right and one guy is going to the left. What will you do in the middle? You will catch both of them, and if you think about a spring, if it was a spring, what would the spring would do? The blocks would go like this and the springs will stretch like this. You don't like both of them going away. You stop both of them. You oppose both of them. So friction on A will be backward, friction on B will be forward. I hope the spring thing is making sense. You just have to imagine there's a spring between them and see how it is stretching. If the spring is stretching, it will pull and then you're done. So you will oppose both of them in this case. What if you have acceleration and speed? Now, what do you think will happen? So the first priority is always velocities. If velocities are same, then we look at accelerations. Because next moment, B will go faster than A. So velocities will all get first priority. If the velocities are not same, it doesn't matter what is the acceleration. If velocities are same, then compare accelerations. We can clearly see B is having more acceleration. Next moment, you're going to go faster. So you will support A, who is going slower, and you'll oppose B. Clear? What about this one? What about this guy? This is the good case. This really tells you the nature of friction. Like I said, friction doesn't care about what are the velocities, and it has only one job in life. It doesn't like them having relative motion. So look at this picture here. If you find a time when velocity at A becomes velocity of B, this will be like UA plus acceleration of A into time plus UB plus acceleration of B into time. The UA will be 6 and this will be T and UB will be 2 and this will be 2T. We clearly see T is equal to 4 seconds. At 4 seconds, both the velocities become same. That means at T less than 4, right, A is still going faster than B. So the friction will say, oh, A is going faster, B is going slower. So I will oppose this guy A and I will support B. At T is equal to 4 seconds, momentarily you will get a 0 there, but the moment you go this, speed of B becomes greater than A. Friction doesn't care. Friction has only one job in the life. It will say now B is going slower. B is going faster. I will oppose B and I'll support A. So you have a friction which is changing with time. This is the reason why we have a separate chapter for it. Did you ever had dealt with a force which changed in the middle of the problem? Mg was always down. Tension was always in one direction. Normal reaction was always the same. Till now, we never dealt with a force whose direction would have changed in the middle of a problem. Friction does this. It's like a rogue force. Like that's why it deserves a one chapter. Is this making sense, everyone? It doesn't care what is the force, what is the acceleration, nothing. It will only see one thing, who is going faster, and then you're done. Let's see one last thing, case 7. If you got this, I think then you got it. The case 7 is not exactly nothing new. It is a combination of all. All surfaces are rough. Find the friction on ABCD. Now, all need to remember is this. Listen, when I talk about friction between A and B, this friction, right? Look at this friction here. It has only one job. It will say, I want to make sure A and B will go together. I don't care what is happening between B and C. I don't care happening between C and D and A and ground. Every surface will only think about its own two surfaces. Is that clear? That's it. The surfaces don't care about the other guy. They all are like, okay, my surfaces, I'll keep them together. What happens to the other guy? It's not my problem. Now, if you think that way, this will belong to 6 cases mein aayega. Matlab, it will be one of the 6 cases. Try, I'll give you a minute. Whatever you think you do, don't worry about right and wrong. I'll show you, then you can verify. Let's see, let's start from the top. So if you do between A and B, so between A and B, who is going faster? A is going faster, so this friction will say, I will oppose this thing and I'll support this guy. Newton's third law. Now between B and C, this looks like case 4, so both are going opposite. So this friction will be backward. This will be backward. Now between C and D, who is going faster? C is going faster, so this will be F3 and this will be F3 and this will be F4. Every surface will have its own different friction. Please look at the directions. So when you talk about B and C, that friction will only look at B and C. Oh, B is going right, C is going left. I'll stop both of them. So oppose B and oppose C. That's it. It doesn't care what F1, F4, and what others are doing. Is this clear, everyone? There. If you understood the 7 cases, now you know how to find the direction of friction. Everything will fall under this one of this category. Any doubts on the direction part? Clear? The next thing, finding the magnitude. Now, this comes from an experiment actually. So people did an experiment. We took a block of mass m on a rough surface. We kept a bucket here where we could put some sand. So you can keep on adding the sand into the bucket or remove the sand. So you can change the mass of this bucket. So this weight will be small mg, which is variable. By adding and removing sand, we can change the small mg. This will be tension. The same tension will act on this. And yeah, obviously to stop this, friction must be backward. And this is the normal reaction. This is the mg. These are all the forces that we have. Now, when we did the experiment, what did we see? See, it is always like that. You do an experiment, you get a data, and from there you try to figure out. As mass m, which is the sand, increases. So as you put the sand little, we observe block does not move. Isn't great? Up to a certain value. And that is interesting because if you look at the tension, T is equal to mg. Since the block is not moving, friction must be equal to tension, and that means friction is equal to mg. That means as you put the sand, m is increasing, so friction is also increasing. So that means this frictional force is not constant. This frictional force is somehow reacting to the mass outside. Friction increases. And after a certain value, if you keep on exceeding a value, right, then it suddenly drops. After a certain value, it block suddenly accelerates. Block, doesn't just move; it accelerates. Something happened to the friction. Think of like this: you're trying to run away, and your friend is catching your hand and not leaving you. You're pushing, you're pulling, your friend is not leaving. You're pulling, your friend is not leaving. Then suddenly they leave you. What will happen? You'll just fly off, right? Something similar. The block feels like that, like this friction just left me like. And when you actually plot this graph, the graph will give you the information what is happening. So when you plot a graph between the friction versus the mass m, the sand, this is what we notice. The friction is increasing gradually, and then it drops, and then it becomes constant. So this is O, this is A, this is B, and so on. So this O to A line is called static friction. Static meaning there is no motion between the surfaces in this scenario. This is the kinetic friction. This is the friction when there is a relative motion between them. So static meaning there's no slipping. So we'll talk about that. And this A value here, this is your F static max. That's a peak value. Yeah, but let's try to understand why this graph is coming this way. So look at the experiment. So when you go from O to A, the block does not move. Basically, there's no relative motion or does not have relative motion. That means the friction is increasing with what you're giving. So if you see, friction is not trying to give everything. It is trying to give what is required. And then something interesting happens at A. At A, we get maximum friction. The block is on the verge of slipping. The interesting part is, why does it decrease? The reason is this. Tell me one thing. Let's say if I'm standing there and you're catching me, okay? And if I try to run away, you're holding me back. Case two, I'm running already and you're trying to catch me when I'm running. In which case do you get a better grip? When I'm standing and you're catching me, or when I'm running and you're trying to catch me? When I'm at rest with you, right, and you're catching me, that is when you can catch me strongly, isn't it? The moment I started running and you try to catch me, your hands will slip, you will not get a better grip. So what happens is, the moment the block starts moving, the bonds which are made, they're all broken. As it keeps going forward, the molecules are trying to form a new bond, but they're not getting enough time to form bonds. If you're getting it, it is like a person is running and you're trying to catch him. It becomes a little slippery. You won't get a better grip. The the molecules are trying to make a bond, but you're not giving them enough time. So the moment the block starts moving, the friction actually decreases because the old bonds are broken and the new bonds are not as strong as the old ones. So in AB, friction drops. When surfaces move, all those cold welding joints are broken. That's why it moves. So this molecule will go and fall on the molecule ahead, but you don't have enough time. You're moving, so you don't form a proper bond. The bonds are broken. It's like to catch a running person. You don't get a better grip, and you do not have enough time to form bonds completely. This results in weaker bonds. They do form something, but it's not really as strong as the previous one. But yeah, if you can stop the block for a moment, they will form completely, and then again friction increases. Therefore, friction, that's the reason why the friction suddenly drops when the block starts moving. And because the friction suddenly dropped, this block will suddenly get an acceleration. And after B, the block is in motion. The friction, yeah, anyway, has decreased. It will maintain that value. So the bonds are breaking, forming continuously. And these bonds are not really as strong as before. So block moves and friction again, you get a constant value, which is lower than the maximum value. This friction is called kinetic friction because you're moving, or there's a relative motion. Is this making sense, everyone? That's your whole story and what is happening with your block. So when people tried this experiment, right, and they found the values, so the forces were like this. So this was your tension, and this was your F, normal reaction, and N. What these people found out, the maximum friction static is proportional to normal reaction. Yeah, obviously, bigger the block, that more friction, you needed more force. But remember, this is the maximum value. This is the max friction before slipping. We have to be a little careful here. Friction is different from max friction. Now, when you remove the proportionality constant, we get F static max is equal to mu static. Now, we have to be careful here. Put a mod. Getting it? These are magnitudes. Think about it. Friction is on the left-hand side, normal is upward. Both are perpendicular. Clear with this? So F bar is not equal to mu as N bar. So F bar is actually perpendicular to N bar. So don't equate the vectors, equate the magnitudes. So that's your relation there. And mu s here is called coefficient of static friction. So we got this from experiment. This is the maximum possible value. This is the maximum possible value, okay? So if I just put it down, so F static max is mu s n. This is right. But if someone asks you what is the friction, F static is less than equal to mu s n. Because just look at the graph here, huh? This entire value, right? You're not slipping anywhere from O to A. And I'll give another example there. And, F kinetic, so this is the friction when you're slipping. Again, this is also equal to something called mu k n. So there are three different frictions, Fs max, Fs, Fk. Fs max and Fs are not same. I'll tell you something about it. This is coefficient of kinetic friction. There's also something called rolling friction and all. We'll see later on, mu s is greater than mu k. We saw the reason why. So let me give an analogy, okay? What is Fs max and what is Fs? Think of like this. Let's say you have 1 lakh rupees with you. And you're ready to give it to me. You're a good person. You're like, okay to give it to me. Okay? I ask you 20,000. How much will you give me? 20,000, right? But you have 1 lakh, right? Okay. If I ask you 50,000, you'll give 50, right? But you have 1 lakh, isn't it? Okay. 90,000, you'll give 90,000. If I ask you for 2 lakhs, you will say, sir, I have 1 lakh, take all this, but I can't give more than this. Did you see something here? Even though you're capable of giving 1 lakh, it doesn't mean you'll give 1 lakh. You will give only whatever was required. When I asked you for 20,000, you can give 1 lakh, but the requirement was only 20. So friction ka job was not to give the maximum friction. Friction ka job was to see what was the requirement and give how much is required. Again, remember, what is friction ka job? To avoid slipping. That's it. It is never about giving full value. So if I show you in numbers, look at this. This is the thing most people mess up. They write F is equal to mu s. That's a blunder. Friction ka job was not to give you maximum value. Look at this thing. Let's say F is equal to 5 newtons. And let's say mu s is 0.5. So this is how you should always check. So here the normal reaction, if I draw the FBT, this is F is 5 newtons, friction will be backward. This is a normal reaction, and this was 50 newtons. N is 50. Fs max is mu s n. That is true, which is 0.5 into 50, which is 25 newtons. So friction is saying I can give you up to 25. It never said I'm giving you this. Up to 25, I can give you. Or if you give me 25, then I will let you move. But now you tell me, if friction gives 25, what do you think will happen? The block will go backward. Did you ever see that thing? You push the dining table and dining table is coming towards you. That would be a big horror movie, isn't it? First thing will start running from there. Now, but just think about the scenario. If F is 25 is acting backward and the block is going backward, who is making the block go backward? Friction. And what was your job in the first place? To make sure there is no slipping. And what the hell did you do? You made the block move. Did you get the problem? Your job was never to go 25. So then you'll go and ask the block, okay, see, I don't want you to move. So how much you need? Block will say, I need only 5 newtons. I said, fair enough, I'll give you 5 then. Right? Why should I give 25 when I can give 5 and get the job done? This is the same thing I was telling you. You have 1 lakh rupees. You're ready to give 1 lakh to me. But I came and asked you only 20 lakh, 20,000. Why will you give me 1 lakh when I'm asking you for 20,000? Is that making sense? That's the difference. That's the difference between FS max and FS. Yeah, I think if you understood that, you know how to find the friction maximum value, the value of friction. We need only 5 newtons to stop slipping. Right, but it can provide 25. Whenever you get confused about that, think about that 1 lakh example. Just because you can give doesn't mean you will give. You will see what is the requirement. So the answer here is 5 newtons only. You don't give 25. I hope that's making sense. Clear with this? So few theoretical things we can write. F static, right, is always less than or equal to F static max. Static friction can be less than this. Can I say like this? F static is always greater than F kinetic. True or false? F static can be less than, equal to, greater than F kinetic. It can be all. That's because if you just look at the graph here, you'll notice, see, this is F kinetic. If you take a value here, it is small. If I take a value here, it is equal. If I go here, it is more. So static can take any value from 0 to max, and F kinetic is less than max. So I can be equal, I can be less, I can be greater also. And there's one more thing. When you say it is not slipping, what do you mean by not slipping? So this is one thing you should be very clear. You say two surfaces are not slipping if they have no relative motion. People think not slipping matlab not moving. No. Two surfaces are said to be not slipping if relative motion is 0. They can go, they should not have any relative motion. So for example, if this guy is going with 2 meters per second, this guy is also going with 2 meters per second. There's no slipping. They're moving, but they're not slipping. So be careful what is slipping and not slipping. Slipping meaning there is a relative motion. No slipping meaning there's no relative motion. The blocks can still move. And then we also define something called a contact force. Look at the word contact force. This is the force because you are in contact. So whenever you touch a body, you get two forces, normal reaction and friction. Both are coming because of contact. You can think of like this. The vertical component of spring, remember I told you about the spring ka logic? So if I treat this as a spring, how is the force here? This is the force, na, Kx. So Kx ka horizontal component is friction, Kx ka vertical component is normal reaction. You can think of like that. So the springs will generate two forces. So a contact force is nothing but a combination of normal and friction. Be careful with that. So you take the resultant of both of them whenever they say contact force. So I goofed it up. Meaning, when I was writing the exam, they gave contact force is 40 newtons. I thought it is N. N is 40. And in the question they gave G is equal to 9.8. I took G is equal to 10. I did the whole problem. I got answer 3.6. Then I rounded off and I marked 4, which became right. My friends took N is equal to 40, normal reaction. They took G is equal to 9.8. They got 3.4 as an answer. They rounded off to 3 and they got wrong. I was lucky. I did 2 mistakes and I got it right. So that's a normal reaction. I hope this was clear. Now you have an idea how to find the magnitude. You have an idea how to find the direction. Technically, theory is over. This is everything that you need to know about friction. This is everything about friction. Now, we will see equations. You'll get the hang of it. We know how to find the direction and the magnitude. We will draw an FBD. Then we assign accelerations, apply constraint equations, then resolve forces along X and Y axis and solve. The whole thing becomes an NLM. We will see that after the break. So take a break, come back by 9:45. We'll continue from here. Any doubts so far? Chalo, come back by 9:45. Yeah, let's start off. Let's start with the question, everyone. We got a wall here. Mu is 0.4. So if nothing is mentioned, right, assume mu s is equal to mu k. So that's a very common thing. They'll just give one mu there and assume mu s is equal to mu k is equal to mu. So just keep that in mind. Yeah, just to keep your life easy, nothing much. So we got a block here of 2 kg. Gravity is there and someone is applying 100 newtons. Find the contact force. Make mu s 0.4. Get it. Straightforward question. Find the contact force. Any answers? Got an answer? You can type in the chat box with the co-host here. Right, Anna. So step one, remember the story. Yeah, it is still the same. Step one, draw your free body diagram. The game always starts from there. Like I said, it is still an NLM thing. So normal reaction, force F, your own weight mg, which was 20 newtons. Then you have to ask yourself, okay, if there is no friction, what would have happened? The block would have come down. So friction should be upward. Now here, there is one small thing I'll tell you. Never write the friction as Fs max. Unless you're damn sure it is slipping. Never write F max, right? Without being sure that it is slipping. Now, the question is simple. Do you know the block is sliding? We don't know, right? That's it. Whole discussion closed. Don't write F max. The moment you write F max, you're telling boss, I know it is slipping. So never write F max without being sure. So when you take this little precautions, right, you'll be careful. You won't goof up things. So if you don't know whether it is slipping or not, means just put F. That takes care of everything. Done. So it is F only. Perfect. What is a normal reaction? 100. What is Fs max? This is different from F, which I wrote. Fs max is mu s into n, which was 0.4 into 100, which was 40 newtons. So friction is saying, boss, if you give me 40 newtons, then I'll slip. But here, the mg is only 20. So we need only 20 newtons to stop slipping. Just imagine, for a weird reason, if F is 40, what would happen? The block will go up, right? You're pushing the block and the block is climbing the ceiling. You have one weird monster in the house. And it would be interesting to see your face if that happens and you and I both will start running. So therefore, friction is 20. This is the problem with the friction. Did you see? Friction ka magnitude can change, friction ka direction can change. You have never encountered a force which is as hopeless as this. मतलब कोई डायरेक्शन फिक्स नहीं है, कोई मैग्नीट्यूड फिक्स नहीं है, कुछ भी कर रहे हैं. That's why we have a separate chapter for it. And what is the contact force? Root over n square plus f square. 10,400. So I'll leave it to you. Is that clear, everyone? Easy. Next one. We use 0.2. This is 5 kg. 20 to 2 newtons. 45 degrees. Find the distance moved in 2 seconds. Initially at rest. And like I said, if I don't give you anything, US is equal to mu k is equal to mu. We never add F to anything, Karthik. Contact force is coming because of normal reaction and friction, right? F has nothing to do with the wall. So contact force is a combination of normal reaction and friction. Let's get this. It's a decent mains question, meaning in the mains is an easy one. Let's see. We have some answers. I hope no one got zero. You got zero. You fell into the trap. Uh, okay. Most people looks like you guys got it. 5.6. Step one, draw the free body diagram. I'm telling you again, the story is always the same. You didn't learn anything new. Only thing you learned is that friction curve, direction, and magnitude. Everything else is same. So let's write the forces. This will be the vertical component, F sine 45, which was 20, F cos 45, 20, and N is not equal to mg every time. This was 50. And this was normal reaction. Friction will be F. We will always write F. We don't know whether it is slipping or not. And then we will check. So N is equal to 50 minus 20. N is 30 newtons. This is a mistake. If you wrote N 50, then you'll get acceleration 0. What is F max? Mu N. Mu was 0.2. So this was 6 newtons. Perfect. Now we can clearly see here, since F cos 45 is greater than 6 newtons, the block is definitely slipping. Therefore, block is moving. Therefore, F is maximum. Now I'm sure F is maximum. Perfect. And the acceleration is forward. I think at this point, question got over. The 20 minus F max is equal to ma. 20 minus 6 is equal to 5a. Acceleration is 14 by 5. Since the acceleration is constant, S is equal to ut plus half at square. U is 0 plus half. 14 by 5 and 2 cos square. 28 by 5 meters. Clear with this? Next one. This is x is equal to 0. We got a block here of mass m. So this surface, right, has a variable friction where mu is equal to e power minus x. X is the x coordinate. When you look at this friction, as x is increasing, the friction is decreasing. When x is 0, friction mu is equal to 1. If x is infinity, e power minus infinity is 1 by e power infinity. E power infinity is a big number, which is 1 by infinity, which is 0. Means as you go more and more to the right, the friction drops. I hope everyone knows this. E is exponential, 2.713, and e power ax dx is 1 by a e power ax. So this much integration you should know. So the question is, someone kicked the block with speed u. Find u if the block never stops. And remember, mu will be a dimensionless quantity because it's a ratio of two forces. So you kept a block on a surface whose friction is varying with e power minus x, and if you kick it, it would generally stop, but this is a special surface. There is a way you can, if you kick with the minimum speed, it will never stop. Others, do keep your cams on. We did something like this in some other chapter. Remember, we called it escape velocity. किसी को याद है question क्या था? Every 10 meters, the gravity was becoming half. Yeah, it's not exactly same thing, but kind of this question, if you remember. Let's see how we approach this. It looks weird and scary, but this is mostly a kinematics problem. So give it a try. Yeah, we can do it, Ahana. That also works. Right? Anyone else? Okay, let's see. Step 1, draw the free body diagram. Normal reaction, mg. Friction is maximum. Now I'm sure why. The block had initially velocity. Initially, it is going with speed u and the ground is not moving. So there is a relative motion. It is slipping. That is the meaning of slipping. If the surface you're touching does not have the same velocity as you're slipping. That's it. There is nothing there. And your acceleration is backward. So since the friction is maximum, F max is equal to ma. F max is mu mg ma. So we get acceleration is equal to mu g. Mu is given as e power minus x into g. Perfect. We got the acceleration. Then A becomes minus dv by dx because it's decelerating. You can see A and V are opposite. If they're in the same direction, I would have written plus. And then, or you can do even better. F is equal to minus ma, and then we will say, I'll assume A also in this direction as forward. Doesn't matter, like just a matter of playing with the minus sign. So then when you do this, you get a minus sign here and a minus sign here. And then we write acceleration is v dv by dx. So if you write A and U in the same direction, then A is plus v dv by du. A and U are opposite, then you put a minus sign. But in max, right, it is always like we assume A and U are the forward direction, so nothing much. So A is v dv by dx. At this point, friction chapter got over. This is all kinematics. So v dv minus g e power minus x dx. Integrate. Initial speed is 0. Initial error at 0. You want to go to infinity. I can directly put infinity here, but let me do with x and then see what happens. So this would be v square minus u square by 2. This will be minus g, and we get a minus 1 e power minus x. Limits will go from 0 to x. V square minus u square by 2 is equal to g into e power minus x minus e power 0. Putting 0 to infinity is easy, but what if they ask you find the distance traveled when the speed becomes half? So this will be useful. So this will be u square plus 2g into e power minus x minus 1. This is your velocity, and since it never stops, your v square must be 0. V must be greater than or equal to 0. So u square plus 2g, I'll put a minus sign there, 2g, 1 into e power minus x is greater than or equal to 0. So that is x is infinity. If you never stop, you're going till infinity. So this will be e power minus infinity. And I hope everyone knows e power minus infinity is 1 by e power infinity. E power infinity is a big number, so that's 1 by infinity, which is 0. So you end up with u square minus 2g into 1 minus 0. We get u square is greater than 2g. We get u is greater than or equal to root 20. So the minimum speed is root 20. So the moment you wrote f is equal to f max, friction got over. After that, this is all kinematics integration. Is this clear, everyone? Clear with this? Let's see one more. Clear, na, Ananya? Dhruv, Rohit? Rohit? Rohit, are you there? Rohit, you're not there. Okay, let me remove him from the classroom. Great. Let's see another one. We got 2 blocks here. This is 3 kg. This is 2 kg. Here the friction is mu 0.2. Here the friction mu is 0.3. And you're applying a force F and gravity is there. So the question is, find the minimum value of F so that none of the blocks slip. Everyone is safe. You don't want 2 kg to slide. You don't want 3 kg to slide. Find minimum F if there is no slipping at any surface. I hope you're able to visualize how it is. It's like you put a book on the wall and put one more book on the wall and you're pushing both the books against the wall. Isn't that how it looks? It's like you took two books and you're pushing them against the wall. If there is no slipping at any surface. Let's give it a try. Hmm. That looks too less actually. Not sure though. The 66.7. I don't know. Let's see. Anyone else? We have two different answers. I'll give a minute more and then I'll show you. Yeah, 60. I don't know. 60 looks very small. So just a gut feeling though. It could be wrong. Anyone else? 66.7. Okay, maybe most are getting 66.7. Okay, let's see. Step one, draw the free body diagram. I'll draw the 2 kg guy first. So this is force F, and this is your normal reaction N1, your own weight at 20. This is friction F1. Nothing is maximum. I don't know, right? Then F is equal to N1 because it's not moving. F1 is equal to 20. Now see, you're not moving. The F1 is 20. That's it. Don't write MUSN and all. F1 is less than 20. Since it is not slipping, it should be definitely less than equal to mu N1. Getting it? If it is not slipping, friction is less than maximum. So we will get 20 is less than equal to, this mu is 0.3 into F. So we got F is greater than equal to 200 by 3. Yeah, this is 66.77. So this is saying if you give me 200 by 3, I will make sure 2 kg won't slip. See, this is not the answer. This is what the system is telling you. If you give me 200 by 3, I'll make sure 2 kg is not slipping. Now let's see what the other guy says. If I draw the FBD for 3 kg, this is N1. This F1 will be acting down, Newton's third law. So if I drag you up, you will drag me down. This will be F2, this will be N2, and this will be 30. So we can clearly see here F2 minus F1 is 30, but I already know F1 is 20. F2 is 50. You're not slipping, so this should be less than equal to mu N2. Here mu is 0.2. N2 is also equal to F only. So N1 is equal to N2 is equal to F. So here I got F is greater than equal to 250. So this is telling me, boss, if you give me 250, I'll make sure 3 kg won't slip. See, they don't know about each other. 2 kg does not know what 3 is doing. 3 kg doesn't know what 2 is doing. Everyone got their answers respectively thinking about themselves. Now you tell me, how much should I give so that no one slips? 250, right? If I give 250, 3 kg won't slip. If I give less than 250, maybe 2 kg won't slip, but 3 kg will slip. Yeah, so therefore, if f is greater than or equal to 250, no one slips. You take the bigger value. Answer is 250. Is that logic making sense? So F1 is 20C. This is true. How did I get this from? This I got from free body diagram. Since it is not moving, F1 is 20. This should be less than or equal to mu n1. So F1 must be less than or equal to F1 max. Simple reason why there's no slipping. If you're not slipping, you're definitely less than maximum. So the only value you know, friction is mu s n only for maximum. If it is not maximum, you don't know what is the value. We need to figure it out. Is this making sense, everyone? Clear with the question? If you see, we have to draw the free body diagram. Friction ka direction is the easy part. The magnitude, you have to be careful. Every time you have to keep telling yourself, oh, is it slipping? No, it's not slipping. Then fine. Then F is not mu s n, F is something else. Whatever is that value is always less than F mu s n. So keep this simple thing in mind. Someone asks you what is friction, never say equal to mu s n. Always say less than equal to mu s n. As long as you remember that one point, at least you will keep asking yourself, is it less or what? Let's do one more. We got a block of mass m here. This side surface is rough. The length of the block is L. The left side is smooth. So look at this block here. Exactly at that interface, right? Left side of the block is smooth. The right side of the line is rough. Then you kick this block with speed u. The block is given speed u. Assume the block completely enters the rough side. Meaning, see, there is a possibility this block can get stuck like this, na? Some part rough, some part smooth. There is a chance. So let's say you are given enough velocity. Assume block completely enters the rough region. Find the distance traveled till it stops. This is a good one. So if you take this block, what is the distance traveled by the block? So before starting the problem, right, always ask yourself, how many different things are happening? How many different situations are happening? So there are two different situations. Situation one, some part is on smooth and some part is on rough. Situation two, you have completely entered inside, you're fully on rough. These are the two situations, isn't it? So there is some time when you're entering, there is some time when you're completely inside. Let's see how will you handle this. It just crosses the smooth region means what? You're already on the border, right? The moment you move little, you will suddenly enter the rough surface, right? I'm not clear, Yukti, what you asked. You are saying it will just stop at the border, ऐसा बोल रहे हो? हाँ, that is same as that only, na? Completely entered, you just stopped. That is okay. So that's like a case where you're on the border of both the sides. So that is okay. So I can ask you that question also. Find the speed such that the block exactly stops at the border. But assume it is crossing inside, it is gone inside like this. So, and then I won't ask you L, na? Then I'll ask you find speed. I will ask you L then. How do we approach this? This is a good one, everyone. Think. There's only one thing at Audi today. F is less than equal to mu mg and direction. Boss. U by 2 friction constant G. But Ahana, after that, do you think it'll come to rest once it enters? It will still have some speed, right? After entering the rough region, it is still going forward. It is still getting dragged. Think for a minute, then I'll show you the steps. Final velocity will be 0. It will travel a little more and then it will be 0. Okay, let's see. Step 1, free body diagram. So let's take the scenario where you have gone little inside. So let's say the block is like this. So the idea here is this, everyone. The friction will come only due to this part, which is on the rough surface. Agreed? The whole normal reaction will not be responsible for friction now. This will behave as if there are two blocks now, one block on the left side and one block on the right side. So let this thing be X. So friction on the block is only due to the region on the rough part. You will not get the friction due to the full block. Friction on the block is due to the shaded part. That means you can't take the total weight there. So what is the mass of the shaded part? Let the mass of the shaded part be equal to small m. Unitary method. For length L, we have capital M. For X, we have small m. We have done this in tensions before, if you remember. The tension in a rope, M by Lx. So now when you draw the free body diagram, this is the normal reaction. This weight will be small mg, you should not put full mg nahi dalna hai. And the friction is backward. So now when you draw the free body diagram, the forces, this friction will be backward. It is slipping because you are going with a velocity, which is mu into small m into g. And the acceleration is forward. Now we'll just take backward. Velocity is u. So we get F max is equal to, now here, look at this thing. Even though you will take the mass of the shaded part, you should take acceleration for total mass. So this will be mu m by L x g is equal to ma. So we get an acceleration which is mu x g by L. You don't have a constant acceleration, everyone. Your acceleration is changing. The more you enter, more friction you get, the more deceleration you have. So this is the acceleration of the block while entering. Because as it goes more and more into the right side, you get more and more friction because more part is on the rough region. Yeah, so can't contract. So that is the reason it will feel acceleration. That's why I took total mass m, no? That's the reason we took total mass m. I didn't take mass of only that part. The friction will be only on the right hand side. Yeah, technically, if it is not a rigid body, this block will have a tendency to compress. But yeah, that doesn't matter. Right, Karthik? Any doubts till this part? So the friction is coming only because of the part which is entering the rough region. Actually, a lot of weird things will happen. This block will try to rotate and topple and all. We'll not get into that. Then, so we got acceleration is equal to mu g by L into x. Since you're decelerating, it's minus v dv by dx is equal to mu g by Lx. V dv minus mu g by L x dx. Limits, initially your speed is u, this is the speed v, this limits will go from 0 to L. Remember, you have to take it only till you enter the surface. So this guy will be v square minus u square by 2 is equal to minus mu g by L x square by 2 limits 0 to L. V square minus u square, 2 will cancel, will be minus mu g L. V is equal to root over u square minus mu g L. What is this? This is the speed just after entering. So when the block has just entered, we get the speed v. U square minus mu gl. This is the speed when you just enter the surface. Just after block enters. Now, this is where that question comes. Now, Yukti, you're saying, na, suppose agar ye b 0 le liya, then you'll get u square is equal to mu gl. Na? Means if you give this much speed, you will just enter the border and stop there. So that could be another question. Find the minimum speed required so that it just enters. Then the second question will be, if I give 2 times the minimum speed, then how much will it travel? But anyway, once you have completely entered, your life becomes easy because this is all rough surface. Yeah, the friction will be maximum, which will be mu capital mg total weight. This will be your acceleration. So A will be mu g. Your speed was v. Now you're asking when will it stop? So it will travel somewhere till here and it will come to rest. So then we use the formula v final square minus v initial square is 2as. Now I can use this because a is constant. This is 0 and v square will be u square minus mu g L. This will be 2. Acceleration is minus mu g into s. So s will be u square by 2 mu g minus L by 2. This is the distance traveled on rough surface. After entering the rough surface, you travel this much. So what is the total distance you traveled? Initially, you traveled L and then you traveled this thing. So let me show you the picture, how it looks. This is how it was initially. This is how it was finally. You can choose any one point. I will just look at this guy here, A. Let's call this guy A. This is A. So if you see, you traveled L here, then you traveled S here. So every point on the block traveled L plus S. Which is u square by 2 mu g plus L by 2. Yeah, this is true when you satisfy v greater than 0. Valid if u is greater than root gl. Yeah, if you're less than this, you won't even enter the rough region. Is this making sense, everyone? So there are two parts of the question. When you're entering, you have a variable acceleration. After entering, you have a constant acceleration. And I hope this maska part, how I took, you understood this maska part? This we did in NLMA, this problem, if you remember. Finding tensions. Where is this guy? Yeah, this questions, if you remember. We took the front part, then we said iska mass is, small m, then we got ml by x, and we did something similar. This is what I keep telling. You will use different parts of different chapters. So, but everything's clear so far. There, today we did all theory and little basic ones. Wednesday, when we catch up, we will do more. We will do much better problems. We will take some tougher ones. It's a small chapter. Meaning, like I said, whatever I taught you today, that is a theory. If you got that, I think then you're done, basically. So maybe you should take another 2.5 classes. We'll wrap up with that. And then after that, we'll start up with circular motion. So yeah, do finish your NLM. If you have any pending, don't keep it for long. Okay, with that, we'll wrap up for that day. I'll see you guys on Wednesday, same time. So do remember there's a test online till Friday. So make sure to give it. So any doubts, anything else, please stay back and ask, or else you're free to leave.